Next we shall start Unit 4, which deals with three-phase circuits. In that the first topic is Introduction to AC circuit. What is an AC circuit? So it is a circuit in which excitation source is AC. That means the circuit is excited by periodic waveform. Most commonly used periodic waveform or periodic function is the sinusoidal periodic function. So this is the diagram of periodic sinusoidal waveform. So x-axis is angle, it is omega t. Y-axis it may be voltage or current. So here we have shown voltage. So this is your sinusoidal waveform. Here we have two consecutive peaks. This is one peak, this is another peak. That distance is called period. The reciprocal of period is nothing but frequency, f equal to 1 divided by t hertz. Any point on this waveform, the corresponding voltage, for example this point, the corresponding voltage is say V1. This is called instantaneous value. The instantaneous values are represented by small letters, that is lowercase letters. So this thing is called one cycle. So this is one cycle, that is from 0 to 2 pi. 0 to pi is half cycle, pi to 2 pi is another half cycle. Above the x-axis this is positive half cycle, below x-axis this is negative half cycle. Again this is positive half cycle. Okay. So this is positive peak, this is negative peak. So this distance, it is called peak to peak voltage or peak to peak value, right? And from the base, the peak or maximum, that distance is called Vm, which is nothing but maximum value or amplitude. So Vm or maximum value equal to peak value divided by 2. Peak to peak value divided by 2. So your AC quantity may be a voltage or it may be current. So if it is voltage, it is represented by V equal to Vm sin omega t, mostly sinusoidal as I told. If it is a current excitation, I, small I, equal to Im sin omega t. Here Im is the maximum value, again Vm is the maximum value, right? So in an AC circuit, quantities can be represented by phasors. What is a phasor? Phasor is nothing but a rotating vector in space. For example, say this is a voltage phasor. This is starting position. Suppose if this phasor is moved in this direction, clockwise direction, after some time, that is after pi by 2 or 90 degrees, it reaches this position. So the path traced by this phasor is like this. Okay. If this phasor rotates 180 degrees, half cycle will be completed. When it completes another 180 degree, another half cycle will be completed. So this is your rotating phasor, actually rotating vector, we call it as phasor. This is your corresponding waveform. So therefore, an AC circuit can be analyzed by means of a phasor diagram. Next you have average value, and all these things we discuss with respect to sinusoidal waveform, because That is what we are going to use almost 99% in our analysis. Okay, so average value. So the average value by definition is nothing but area under the half curve, half sinusoidal, half cycle divided by the length of the cycle. So it means, see this sinusoidal waveform, positive half cycle and negative half cycle. So these two are symmetrical. So if you take the average value for this, it will become 0. So you cannot find average value for the entire waveform. So normally what they will do is, for average value you take half of this cycle. Okay. So you find area under this curve divided by the length of the curve. So this case phi is the length of the curve. So to find this area we are making use of integration. So integral, so this is nothing but V. So area under this curve is this integration, integral 0 to pi V d omega t divided by the length of the curve base. Actually it is length of the curve base. So this is the length of the curve base. So it is pi. So V average equal to 1 divided by pi integral 0 to pi V d omega dt. So V we already defined as Vm sin omega t. Substitute this here. V average equal to 1 by pi integral 0 to pi Vm sin omega t d of omega t. So this Vm is constant, you take it outside. V average equal to Vm by pi integral 0 to pi sin omega t d of omega t. V average equal to Vm by pi. You integrate this sin omega t, so you get minus cos omega t. Limit, upper limit is phi, lower limit is 0. So this minus you can take outside. V average equal to minus Vm by pi cos omega t, limits 0 to pi. So now you apply the upper and lower limits. V average equal to minus Vm by pi. Apply the upper limit first, cos phi minus cos 0. V average equal to minus Vm by pi. Cos phi is minus 1 minus cos 0 is 1. V average equal to minus Vm by pi, minus 1 minus 2. So now this minus and minus become plus. V average equal to 2 Vm by pi. So this is the expression for average value. So next topic is RMS value. RMS value. What is RMS? RMS means root mean square value. Sometimes it is also called effective value. For a sinusoidal wave, it is given by Vrms equal to square root of 1 by 2 pi integral 0 to 2 pi V square d omega t. So V equal to Vm sin omega t. So Vrms equal to, substitute square root of 1 by 2 pi integral 0 to 2 pi Vm sin omega t the whole square d omega t. Next you square the term. Vrms equal to square root of 1 divided by 2 pi integral 0 to 2 pi Vm square sin square omega t d omega t. Vm square is a constant, take it outside. Vrms equal to square root of Vm square divided by 2 pi integral 0 to 2 pi sin square omega t d omega t. So this I split the square root into 2. Vrms equal to square root of Vm square by 2 pi multiplied by square root of integral 0 to 2 pi sine square omega t d omega t. Vrms equal to square root of Vm square divided by pi square root of integral 0 to 2 pi. The sine square omega t you can write, it is a trigonometric identity. You can write 1 minus cos 2 omega t divided by 2 d omega t. So this 2 is a constant, you can take it outside the integration. So you get the next step. Next step is going to be Vrms equal to square root of Vm square divided by 2 pi multiplied by square root of 1 by 2 integral 0 to 2 pi 1 minus cos 2 omega t d omega t. Vrms equal to square root of Vm square divided by 2 pi square root of 1 by 2. So I can split this integrals into two parts. First one is going to be integral 0 to 2 pi d omega t minus integral 0 to 2 pi cos 2 omega t d omega t. Vrms equal to square root of Vm square divided by 2 pi square root of 1 by 2. Now you integrate this. If you integrate d omega t, you get omega t with the limit 0 to 2 pi. And then cos 2 omega t, if you integrate, you get sin 2 omega t divided by 2, 0 to 2 pi. So Vrms equal to Vm square root of Vm square divided by 2 pi square root of 1 by 2, apply the upper limit 2 pi, apply the lower limit minus 0. Here also minus sin 2 into 2 pi divided by 2, apply the lower limit minus sin 2 into 0 divided by 2. So next what we get? Vrms equal to square root of Vm square divided by 2 pi square root of 1 by 2, 2 pi minus sin 4 pi by 2 minus sin 0 divided by 2. Vrms equal to square root of Vm square divided by 2 pi square root of 1 by 2, 2 pi. See, sin 0 is 0, so this term will become 0. This is sin even number of pi, sin 2 pi, 4 pi, 6 pi, that is also going to be 0. So these two terms will become 0. So next we have Vrms equal to square root of Vm square divided by 2 pi square root of 2 pi divided by 2, this 2 getting cancelled. Vrms equal to this, I can split into two square roots. Square root of Vm square divided by square root of 2 pi multiplied by square root of pi. So this I can write square root of Vm square, this I can divide into 2, that is I can split into 2, that is square root of 2 multiplied by square root of pi multiplied by square root of pi. So this pi and pi getting cancelled. So you take square root of this, square root of Vm square is going to be Vm root 2 as it is. So Vrms equal to Vm by root 2. So this is the expression for RMS value of a sinusoidal waveform. Next we shall recall the concept of phase. Concept of phase. So this is very important. See here, I have one waveform A. This I call reference waveform, right? This is a reference waveform. Also I have one waveform B, this green color, this brown color, waveform C. All are sinusoidal waveforms. Okay. Suppose this is your reference. This is a starting point. Suppose this is your reference waveform. A is your reference waveform. If you look at C, suppose this is a starting point. This has started minus 90 degrees. That is some angle before the starting of this reference waveform A. So it has started at minus pi by 2, well ahead of the starting of this waveform A. So I can say this waveform C leads A by 90 degrees. Waveform C leads A by 90 degrees. Something like this. See, when A is just about to start, this C has already reached the maximum value. Okay. It is like two people are running, right? Say for example, somebody, the A is A, B, C, these three people are running. Just imagine on a running race, B is in the middle, right? Suppose C, that brown color, all are running, C is some 90 feet. Okay, for example, I am telling 90 feet leading before 90 feet before A. Suppose B is coming behind A, right? Say 90 feet behind A in a running race. Same thing here. Suppose if you take B, right? B just starts after 90 degrees of starting of A. A started at point 0. When A has reached maximum, at that time only B is just going to start. So what we can say is the waveform B lags the waveform A by an angle of 90 degrees or pi by 2 radians. Okay. This you can represent mathematically like this. Suppose A is your reference waveform, VA equal to Vm sin omega t, VB, it is lagging means minus Vm sin of omega t minus 90 degrees, VC, it is a leading, equal to Vm sin of omega t plus 90 degrees. So in general, you can write a waveform like this, Vm sin of omega t plus or minus pi, phi. So this phi is called phase angle. Phase angle is nothing but that this angular difference between two waveforms. It need not be always 90 degrees. So it can be any value. That's why we are putting the common symbol phi. Okay. Next, the phasor diagram, just we will recall. All these things are just a recall. You might have studied AC circuit in basic electrical engineering. Since this is only a recall, right? So I already told you can analyze an AC circuit by using its phasor diagram, right? Suppose I have the AC voltage phasor. Now I am talking in terms of phasor. We represent phasor using capital letters. For instantaneous value, we use small letters or lowercase letters. For average and RMS value, we use uppercase letters. And to represent phasors, again we are using the capital letters or uppercase letters. For example, you consider one voltage source connected with the resistor. So I is the current phasor flowing in the circuit. In a resistor, suppose these phasors are rotating in the anti-clockwise. Normally, we will show phasors rotating in the anti-clockwise direction. Now, this voltage V and this current I, both are lying on each other. So there is no angular difference between the voltage and current. So we can say that in a resistor, when you apply AC signal, sinusoidal AC signal to a resistor, both voltage and current are said to be in phase. In other words, there is no phase difference between voltage and current in a purely resistive circuit. Next, you consider a voltage source, and we have one inductor. So V is the voltage, I is the current. You have only a pure inductor. The phasor diagram will be like this. Suppose this is your voltage. This is a point 0. Current will be after that. Suppose this phasor is rotating in the anti-clockwise direction. Normally it will rotate in the anti-clockwise direction. First is this voltage followed by this current. So I can say in a pure inductance, current lags voltage by 90 degrees. Current lags voltage by 90 degrees. So we say something is leading or lagging in terms of current. Normally we say in terms of current. So here we are seeing current is just lagging behind this voltage by an angle of 90 degrees. Now you consider a pure capacitor. We have voltage source, capacitor C, this is the current. Here suppose this is your voltage phasor, this is rotating in the anti-clockwise direction. Now the current is ahead of this voltage phasor. How much ahead? 90 degrees or pi by 2 radians. So in this case, the case of a pure capacitance, we say current leads by an angle of 90 degrees. So resistor, these two are in phase. There is no angle between voltage and current. Whereas in a pure inductor, current lags the voltage by an angle of pi by 2 radians or 90 degrees. In the case of a pure capacitive circuit, then current leads the voltage by an angle of 90 degrees or pi by 2 radians. Next we shall see an example, not problem. This is a common thing. That is phasor diagram of RLC circuit. See, sometimes most of the circuit may not be always pure resistor or pure inductor or pure capacitor. So it may be a mixture of all these things. Okay. So mostly it will be all three will be present. So for example, here I have a voltage source. I have R, L, C, all are connected in series. I is the current phasor. So the voltage across resistor R is VR. It's nothing but I into R. Voltage across voltage across L is VL, which is I into XL. XL is the inductive reactance. C, voltage across the capacitor C is VC, which is I into XC. XC is the capacitive reactance. So you can draw the phasor diagram. Here I have taken, this is x-axis, y-axis. So this is current I. So in the resistor, we are voltage across the resistor and the current. Same current is flowing. Both are in phase, no angle. Okay. So in the inductor, the VL, that is leading, this voltage is leading the current by an angle of 90 degrees. and in the capacitor it lags this current by an angle of 90 degrees. Okay. So that's why we are putting this above the x-axis. We are putting this below the x-axis. So VL is I into XL, VC is I into XC. So now suppose this inductive reactance is greater than capacitive reactance. Any one may be dominating. Okay, normally. So therefore VL will be greater than VC. So what we are doing is we are folding this like this. So just we are folding like this. So now this will become minus VC. Okay. So from this VL you subtract this VC because you changed the position. Subtract this VC. So the resultant is going to be, because VL is greater, VL minus VC. Okay. So this is VR, VL. So you can just move this parallelly like this. So you have VR, here VL minus VC. So you have the vector addition. You might have studied in your plus 2. You have the vector addition, that is VR vectorially added with VL minus VC. Not ordinary addition, vector addition. Okay. So the angle, so this VR vector addition of VL minus VC, you get this V, this vector V. So now the angle between this current and this voltage V, it is nothing but the phase angle phi. Phase angle phi. So you can find out, this is a phasor diagram or vector diagram. So we are here VL minus VC. So actually if you move this, you can draw like this, VL minus VC. So you know very well, suppose I want to know this, the magnitude of this V. So it is, what is that theorem? Pythagoras theorem. That is right. It is like a right triangle, right? So magnitude of this is going to be square root of VR square V equal to square root of VR square plus VL minus VC the whole square. V equal to, substitute for VR, VL, VC, square root of IR square plus IXL minus IXC the whole square equal to square root of IR square. I is common, you can take it outside. I into XL minus XC the whole square. V equal to square root of IR whole square. Now separate the square. I square multiplied by XL minus XC the whole square. Now you square this term. V equal to square root of IR square R square plus I square XL minus XC the whole square. So I square is common, you can take it outside. So V equal to square root of I square into R square plus XL minus XC the whole square. Now I split this square root two parts, equal to square root of I square root of R square plus XL minus XC the whole square. So hence V equal to I into Z. Again this is Ohm's law with respect to AC circuit. So here this term, that is called impedance, denoted by the letter Z. Here Z equal to square root of R square plus XL minus XC the whole square, which is called impedance. So V equal to IZ, it is the Ohm's law with respect to AC circuit. Next, we have already seen the that phasor diagram. So if you want, I will show you again. So I can show just for your understanding, not for any other thing. For your understanding, so phi is I think it is visible for you. I will show like this. Here, phi is the phase angle, right? In this, what is tan phi? Tan phi is, what is tan phi? Opposite side by adjacent side. This is from trigonometry. What is opposite side? VL minus VC. Adjacent side is VR. So that is what we are going to make use of. So phase angle phi equal to tan inverse, right? Tan inverse. Actually tan phi is opposite side by adjacent side. VL minus VC divided by R. If you want to know what is phi, you have to take the inverse. So phase angle phi equal to tan inverse VL minus VC divided by VR. Phi equal to tan inverse. So VL is nothing but I into XL minus VC is I into XC divided by VR is I into R. Okay, it is not suffix. This is written very small letters. It is I into R. So this I is common, you can take outside. So phi equal to tan inverse I into XL minus XC divided by R. So this I and I getting cancelled. So this is the expression for your phase angle. Phi equal to tan inverse XL minus XC divided by R. Right? Now, finally, this we can recall. Say this is your voltage phasor. Say this is V is your voltage phasor. Say this is a current phasor. The phase angle may be phi. Okay. Right? So you can see this current I lagging the voltage by an angle of phi. Right? Now this phasor phi, you can resolve into two components. One is called horizontal component, another one is called vertical component. So the horizontal component is I cos phi. This vertical component is I sin phi. Okay. So now we have three types of power. Suppose if you multiply this voltage into current, that is called apparent power, denoted by the letter capital S. X is equal to V into I, volt ampere. This is called apparent power. Next, if you multiply voltage with this horizontal component, that is called capital P, VI cos phi watt. This is the true power. True power is actual power consumed by the circuit. So this is the true power. P equal to VI cos phi watts. Suppose if you multiply this vertical component with this voltage, that is called Q equal to VI sin phi var volt ampere reactive. So this power is called reactive power. S is the apparent power, P is the true power, Q is called reactive power. Okay. So now you can draw the phasor diagram in terms of the resistor and reactances. Okay. Actually this you derive from the voltage, what do you call, I will show you. Same thing I will again show. See, this is VR. This is VL minus VC. So instead of VR, you put IR, IXL minus IXC. So you just take this I outside. So you write in terms of only the reactances, resistance reactance. So this is R. This is going to be XL minus XC. So this is R phase R. This is XL minus XC. So the vector addition or phasor addition, okay, of these two is nothing but Z. This is called your impedance. So this angle is your phase angle, right? This angle is phase angle. What is cos phi in this? Opposite divided by hypotenuse. So cos phi equal to R divided by Z. That is, Z means Z magnitude, right? So this cos phi, it is called power factor. This cos phi is called power factor. So cos phi equal to R divided by Z magnitude. This we have already seen. Root of R square plus XL minus XC the whole square. Okay. So by using these three power, apparent power, true power, reactive power, these three are related by this diagram. It is called a power triangle. This triangle is called a impedance triangle. See, all are phasors. Okay. So here we have a P, that is the real power or true power, and this is your actually this should be like this. These are all phasor, no? This should be like this. Q is the reactive power and S is the apparent power. And again the angle is the phase angle phi. Okay. So now Q by P, suppose if you take the ratio Q by P, Q we already know VI sin phi, P is nothing but P capital P, I'm sorry. P is nothing but VI cos phi. So V and V getting cancelled, I and I getting cancelled, you get sin phi by cos phi, that is nothing but tan phi. So what is the phase angle? Tan phi is nothing but, this is tan phi. So phi equal to tan inverse of Q by P. Okay. And again kVA, mostly it will be in terms of kilowatts. Okay. So it may be kilovolt ampere, kVA. It may be kilowatts. This may be kVAR. Okay. So now this S is nothing but Pythagoras theorem. This is the phasor addition. So kVA. So S is expressed in VAR kVA. So kVA equal to square root of this, square root of square of this, square of this. So kVA equal to square root of kW square plus reactive power kVR the whole square. So these are all some of the recall. So we are not completely studying in this AC circuit because main focus of this unit is three-phase circuit. So this is only a recall of what you might have already studied in previous basic courses, the AC circuit, some of the basic concepts with respect to AC circuit. So what is an AC circuit? What is a sinusoidal source? And then what is a sine waveform? Some of the terms related with the sine waveform, for example, instantaneous value, maximum value or amplitude, time period, peak to peak value, frequency, and then two important terms. One is called average value of a sinusoidal waveform and RMS value of a sinusoidal waveform. And then we have seen what is a phase and what is phase difference. And then phasor diagram. What is a phasor diagram? How it will be in different circuits, resistive circuit, inductive circuit and capacitive circuit. When all these three things are present, RLC circuit, what will be the phasor diagram? And also we have seen power in AC circuit. We have apparent power, true power and reactive power. How these three are related with each other through this power triangle. Also we have seen the impedance triangle, and from the impedance triangle what is power factor and the expression for phase angle.